Hello everyone. In this let us discuss about the angle modulation, that is module 2 or as per VTU syllabus, angle modulation. Myself Deepashri AP. So let us discuss in detail. So what is the frequency modulation? When it comes into the angle modulation, mainly in this topic we are dealing with two modulation types. That is, one is frequency modulation, the other is phase modulation. And as per our syllabus, we have to move deeply into the frequency modulation, and just we should know what is phase modulation. That's it. In this frequency modulation we have to study the basic concepts and the derivations, narrowband FM, wideband FM, generation, demodulation of this, all these things we have to look into detail. Now before going into detail, let us see what is a frequency modulation. So the definition for the frequency modulation here: frequency of the carrier wave is changed in accordance with the message signal. This process is called frequency modulation. So the carrier frequency is varied in accordance with the message signal. So in this case the amplitude will be constant. Amplitude will not be varied. Only the frequency of the carrier is varied in accordance with the message signal. This process is called as frequency modulation. In FM, the carrier amplitude remains constant and the carrier frequency varies. It is a type of angle modulation. So here we can see this is the signal wave or message signal. This is the carrier frequency, and here it is the FM modulated wave. So at this point we can see it is it is at reference point 0. So the frequency, it is of low frequency, and when it reaches this point having the maximum amplitude, so it should have high frequency at this. So the carrier frequency is high at point B. When it reaches the point C, again the frequency, it retains the frequency of A and C. It will be same because the points the same, it lies in the reference point. And as it goes to D, this is the negative maximum, so the frequency becomes again less at this point. So here we can see the wave is little more broader, and as it goes to E, again it will be having the same frequency of A and C, and again when it reaches F here, the frequency, it should be high frequency. In this way we can plot the FM wave. F naught plus delta F and F naught minus delta F, that is a frequency deviation. Like here this is the F naught, that is the frequency of the carrier, resting frequency, and the modulated signal will be varied plus or minus from this frequency. Like here it is plus, and in this case it is minus, low frequency. So that is the frequency deviation occurring in the modulated signal, FM modulated signal. Now coming to the basic definition. Now how to write the equation for the FM modulated wave. First we will look into that. Let theta I of t denote the angle of the modulated sinusoidal carrier at time t. It is assumed to be a function of the information bearing signal or the message signal. So we express the resulting angle modulated wave as AC cos 2 pi FCT plus pi. So angle modulated wave in general we express as AC cos 2 pi FCT plus pi, where AC is the carrier amplitude, A complete oscillation occurs whenever the angle theta I of t changes by 2 pi radians. Now, if theta I of t increases monotonically with the time, here it is shown that in this figure, then the average frequency in hertz over a small interval from t to t plus delta t is given. So if it increases monotonically as per this figure, that is theta of t is theta of t plus delta t. That is the time interval is t to t plus delta t. Then I can write f delta t of t equal to 1 by 2 pi theta of t plus delta t minus theta of t divided by this change I can write it as delta t, because t minus t plus delta t, that is delta t divided by delta t. Allowing the time interval delta t to approach 0 leads to the following definition for the instantaneous frequency of the angle modulated signal. That is fi of t equal to limit delta t tends to 0 f delta t of t. That is if I apply the limit delta t tends to 0, then theta t plus delta t minus theta I of t divided by 2 pi delta t. So I can take this 2 pi outside, 1 by 2 pi d theta I of t divided by dt will be the fi of t. Now an unmodulated carrier, the angle theta I of t is, in case of unmodulated carrier, the angle theta I of t is equal to 2 pi fct plus phi c for m of t equal to 0. There are an infinite number of ways in which the angle may be varied in some manner with the message signal. We shall consider only two commonly used methods, phase modulation and frequency modulation, as defined below. So we will be concentrating only on frequency as well as phase modulation techniques. Now, phase modulation is the form of angle modulation in which the instantaneous angle theta I of t is varied linearly with the message signal. That is, in case of phase modulation, it is a type of angle modulation. Instantaneous angle theta I of t is varied linearly with the message signal, and I can write as theta I of t equal to 2 pi fct plus kp m of t, where 2 pi fct represents the angle of the unmodulated carrier with the constant phi c set equal to 0, and kp is the phase sensitivity factor of the modulator expressed in radian per volt in the assumption of m of t is the voltage waveform. So as per this theta I of t, I can write the s of t equal to ac cos 2 pi fct plus kp m of t will be the equation for the modulated signal of PM wave. Now frequency modulation. So in case of frequency modulation, here the instantaneous frequency is varied linearly with the message signal m of t. So I can write fi of t equal to fc plus kf m of t. Fc represents the frequency of unmodulated carrier. Kf is the frequency sensitivity factor expressed in hertz per volt, that is on the assumption of the voltage waveform. Now integrating fi of t with respect to time and multiplying the result, we will get theta I of t equal to 2 pi integral 0 to t fi of tau d tau. We know that fi of t equal to fc plus kf m of t, and substituting this fi of t here, I can rewrite as 2 pi fct, that is 2 pi fct plus integral 0 to t 2 pi kf here kf is there, 2 pi is common, so I can take it outside, and remaining is m of dot d dot. The second term accounts for the increase or decrease in the instantaneous phase theta I of t due to the message signal m of t. The frequency modulated wave is therefore, that is, S of t equal to AC cos 2 pi fct plus 2 pi kf 0 to t m of dot d dot. So frequency modulated wave equation I can write like this. This will be the frequency modulated wave equation. S of t equal to AC cos 2 pi fct plus 2 pi kf 0 to t m of dot d dot. Narrow band frequency modulation. Now we have to write the equation for the narrow band frequency modulation. Consider then a sinusoidal modulating wave defined by, that is, the message signal is given by m of t equal to am cos 2 pi fmt. Instantaneous frequency of resulting FM wave, that is Fi of t. Instantaneous frequency is given by Fc plus Kf am cos 2 pi fct, or Fc plus delta f cos 2 pi fmt, where delta f equal to Kf into am. So it is the frequency deviation. Delta f is the frequency deviation. Maximum departure of the instantaneous frequency of FM wave from the carrier, that is how much deviation it can take from the frequency of the carrier, that is the frequency deviation. That is theta I of t equal to 2 pi fct plus 2 pi kf 0 to t m of t dt. That is rewriting 2 pi fct plus 2 pi kf 0 to t m of t, that is the message signal am cos 2 pi fmt dt. Now 2 pi fct plus 2 pi kf am divided by deriving integrating this 0 to t cos 2 pi fmt, that is sin 2 pi fm divided by 2 pi fm. 2 pi cancels, so remaining is theta I of t equal to 2 pi fct plus kfam divided by fm. Kfam means we can rewrite it by delta f. So delta f by fm sin 2 pi fmt will be the equation for theta I of t. The ratio of the frequency deviation delta f to the modulation frequency fm is commonly known as modulation index of a FM wave. So delta f by fm is the modulation index of the FM wave, and we denote that by parameter beta. Beta equal to delta f by fm. So I can write theta I of t equal to 2 pi fct plus beta sin 2 pi fmt. So in this, S of t is given by AC cos 2 pi fct plus beta sin 2 pi fmt. So here we can use the trigonometric relation cos, this is A and this one B. So cos A plus B. By using this trigonometric relation, I can rewrite S of t as AC cos 2 pi fct cos beta sin 2 pi fmt minus AC sin 2 pi fct sin beta sin 2 pi fmt. Now by using the approximations, that is cos beta sin 2 pi fmt is equal to 1 and sin beta sin 2 pi fmt equal to beta sin 2 pi fmt. By using this approximation, I can rewrite this S of t as S of t is approximated to AC cos 2 pi fct. This term it becomes 1 since it is approximated to 1 here, and minus again AC sin 2 pi fct here, then sin beta sin 2 pi fmt, it is approximated to beta sin 2 pi fmt. So beta sin 2 pi fmt. So this is the S of t equation after the approximations. So here also we can notice in this term we have sin two terms, two sin terms, that is sin A sin B. So I can use the another another trigonometric relation, sin A sin B equal to 1 by 2 cos A minus B minus 1 by 2 cos A plus B. So S of t, I can rewrite S of t as S of t equal to AC cos 2 pi FCT minus, keeping the first term as it is, now minus beta AC by 2. This truth it is the cos 2 pi Fc minus Fm of t minus beta AC by 2 cos 2 pi Fc plus Fm of t. Now S of t equal to AC cos 2 pi FCT minus beta AC by 2 cos 2 pi FCT plus beta AC by 2 cos 2 pi FMT. The amplitude modulation wave is, so amplitude modulation wave is given here. S of t equal to AC cos 2 pi FCT plus mu AC by 2 cos 2 pi FC minus FM into t plus mu AC by 2 cos 2 pi FC plus FM into t. So between narrowband FM wave, so this is a narrowband FM wave equation. Only the difference is the sign reversal of the lower sideband. Fc minus Fm, it is the lower sideband. Fc plus Fm is the upper sideband of the narrow wave. So here we can see it is minus. Here it is plus in case of lower sideband. So only the difference is the sign reversal of the lower sideband. So here we can see the block diagram of indirect method of generating narrowband FM. Already we discussed the equation for narrowband FM, and here we can see the block diagram for the same. It consists of an integrator, product modulator, and a carrier signal is given to the product modulator as well as the adder by using to the product modulator with the 90-degree phase shift and directly to the adder, and here we will obtain narrowband FM wave. This blocks, product modulator, shifter and adder together, these blocks we call it narrow band phase modulator. And another method, it can also be generated by using a nonlinear device and a narrowband FM wave by passing it to through the nonlinear device and then to the bandpass filter. So the output of that we will get wideband FM. So to generate the wideband FM by with the help of the narrowband FM, we have to use the nonlinear device and we have to pass the narrowband FM wave through nonlinear device and then to band pass filter. So the output will be wideband FM or narrowband FM wave. Just give it into the frequency multiplier which consists of a nonlinear device followed by a band pass filter. So frequency, if we give it to the frequency multiplier which consists of a narrowband device as well as a band pass filter, the output will be wideband FM. This modulator involves splitting the carrier waves into two parts. One part is direct, the other part contains a degree phase shifting network and the product modulator, the combination of which generates a DSP-SC modulated wave. The difference between these two signals produces a narrowband FM but with some amplitude distortion. So it produces a narrowband FM with some type of distortions. So here in this we can see that the comparison of AM and FM wave. Some parameters are given. The comparison is given. Just go through that in detail. It is given the bandwidth, number of side bands, modulation index, what is the modulation index, and how to plot the modulated signal in case of FM and FM and AM, and what are the applications. That is, in case of AM it is broadcasting video transmission in TV. In case of FM, broadcasting broadcasting FM, audio transmission in TV. Next, we can see the comparison between FM and PM, that is frequency and phase modulation. So the parameter, the three comparisons it is given, just we can go through that. Frequency, maximum frequency deviation depends upon the amplitude of the modulating signal and its frequency. Maximum phase deviation depends on amplitude of the modulating signal. Here, frequency of the carrier is modulated by modulating signal. Phase of the carrier is modulated by modulating signal. Modulation index is increased as the modulation frequency is reduced, and vice versa. Modulation index remains same if modulating signal frequency is changed. So these are some of the difference. Thank you.